Hello, everyone. We are Group 10, and we present our hands-on project, how to interpret molecular lines from dense gas in galaxies. Our motivation was to understand the physical conditions of molecular gas in a nearby galaxy, namely NGC 1068, by analyzing two transitions of CO emission. We aim to derive key physical parameters such as gas temperature and column density in regions affected by both star formation and AGN activity. For this, we used the local thermodynamic equilibrium methods, like rotational diagrams, to determine the gas temperature and the column density. And then we linked the observational results to chemical evolution with the astrochemical modeling code, USC-CHEM, to explore how the gas abundance gets affected by these parameters, like density, radiation field, cosmic ray ionization rate, and temperature. Yes, and we determined the values of these parameters that give rise to the observed column densities of CO in this galaxy. So a few words about carbon monoxide. This is the second most abundant molecule in the universe, mainly used to trace molecular gas in the universe. Its rotational transitions from 1 to 0 through 6 to 5 is accessible in ALMA bands 3 to 9. And from its from the CO line intensity, the XCO, the conversion factor can be calculated, which can be used to derive the molecular hydrogen column density. We used ALMA data of NGC 1068. It's a CFR2 active galaxy at a distance of 14.4 megaparsec. And we used the observations of its circumnuclear disk. Here we show the moment zero map of the CO, one of the CO transitions. From this, we chose two regions that are denoted by these green circles. And in these green circles, both of the spectra in these two transitions are shown that from which we derived the line integrals by Gaussian fitting, by fitting a single line. And we analyzed this data with the equation above. From this, we derived the column density and the temperature. At the first step, we used this W parameter, that is the line integral, and approximated this. So we used this equation as if it was a linear equation. And in this, the logarithmic part of the right side of the equation was the intercept of this linear equation. T was the parameter that we were looking for, and the left side was the function itself. From this, we had to only use the gamma U constant and the GU, the degeneracy. The N was the column density, and Z is the partition function. EU is the upper level energy. And from this, we could plot these rotational diagrams seen here. These are from the two regions chosen, and the two blue dots are for the CO transitions. And the fit itself, the linear fit itself, is the temperature. It's important to note here that, of course, two lines can always be fit with a linear fit, but we consulted the literature, and we confirmed that we could use the LTE approximations here. So it was an assumption that we could use in this case. So after that, we only needed to calculate the partition function. Then we could derive the column density from the equation above.
So we're going to use the chemical model, which is called UCL-Chem, and it's a time-dependent gas grain chemical code. It has different modules for different environments, such as molecular clouds, hot cores, and sea. And it enables the user to change the physical conditions and combined with a chemical database such as PETA, we are able to simultaneously treat gas phase reactions and grain surface chemistry, whether in 0D or in 1D. So we have also the addition of a spatial component. So the first thing that we wanted to check is the effect of these different physical parameters on the output of this data. So first of all, we ran the model with these different set of fixed values for the parameters. And we got an input, which is the fractional abundance of CO with respect to H2. If you can see here, the plots, we have the solid lines, which denote the gas phase CO, and the dotted lines that denote the ice phase. And what we did is that we changed these parameters one by one in order to see its effect on the outputs. So we changed the density, the temperature, the cosmic ray ionization rate, and the radiation field. We can see that the density is the parameters that affects the most these outputs. And it is noticeable that the radiation field, which is the last plot, does not affect it that much. And this is quite expected because you're working on a media with relatively high visual extinction. And so the UV cannot even penetrate. So it gets attenuated quite fast at the edges. The second thing that is interesting with this code is that it enables us to trace the major reactions routes that involves the production and the destruction of CO. And we see the production of CO is majorly affected by the reaction of H and HCO on the surface of the ice mantle, which is the formation of CO. And destruction of CO comes from mostly its reaction with H3. But again, this is just one timestamp, and these reaction rates evolve with time. And on the left plot, we see the different species evolution with time that play a role in these reactions. Also, one more thing in the previous plots is that we see that the general trend is that the CO is down, however, the ice phase goes up, and this can be partly attributed to the freeze out of CO on top of the ice mantles. And finally, we wanted to match the observations to the chemical model. And since we're in an optically thin environment, we can do the approximation of transforming the fractional abundance, which is the output of the code, into column density. To do so, we multiply this fractional abundance by the AV times 10 to the power 21, which is the on magnitude. The AV is calculated in a crude way, just per SPF hydrogen, which is the input of So we get the evolution of the column density of CO with respect to time. And by combining it with the column density that we got from the observations, which is 510 to the 18, we can have a very crude estimate on the age of this cloud, 10 to the power 5. Finally, we did a lot of assumptions in this project. So healthy and stuff. So there's a room to error propagation. There's a new error that adds on, which should be considered. We could have also used other CO transitions to have a better fit. And we could also say Galaxy. I'll leave you with the conclusion and thank you for your attention.
Questions? So all this surface chemistry depends a lot on the accumulated surface of the grains and the freezing of molecule and so on. So have you played on the size distribution or is it something fixed?
The size distribution of the grains?
Yes. Okay. Questions? No more questions. Okay, so thank you.